stuff into section on class A.
Don't you like this class too?
No, I like hearing the process about that stuff. It actually like helps. I mean, that's stuff I need to know, so I actually appreciate that class. No offense to this class, but
You'll figure out at some point that this stuff in here might be stuff you
yeah, I mean it might be. You never know.
Can't find these other two.
We're gonna go over. All right, finish up whatever you're on right now as far as that paper goes. Set it off to the side. Have your homework out. We're gonna go over problems off the homework. First, though, I'm gonna go over this quiz. Define, explain, or tell the meaning of each. What's this first one?
Angle.
Angle. I would accept. If you just wrote angle, that's fine. How about this one?
Perpendicular.
Perpendicular. What else would I accept? Forms what? Forms right angles. Something like that would have been fine. Reflexive property. Anything equals itself. Anything equals itself. In past years, I haven't done it this year because we're sort of, we keep running out of time when we're supposed to do it. But in past years, I've given a whole lot more definitions, quizzes, and stuff. Some of them 20 terms long, some of them 5 terms long, some of them whatever. This year I haven't done it. Midpoint formula.
Parentheses x1 plus x2 over 2, comma, y1 plus y2 divided by 2.
How many people should have missed that?
None.
Why?
I got a question.
Literally
I
on
put
the-
X in and Y in. Does it matter? And then I put the X.
Put the rest of it?
Yeah.
It's up there on the board. You shouldn't have missed that one. Angle bisector. What's an angle bisector?
It's an angle that's
Cuts an angle into
It's a ray that's
congruent pieces.
All right, it should say array. I don't care so much. Splits and angle into two congruent angles. This.
Isosceles.
I would accept isosceles triangle. If you spelled isosceles triangle wrong, you know, will I mark it wrong? Probably not. Supplementary angles.
2 side-by-side angles that equal 180 degrees.
2 angles add up to 180 degrees. 2 angles add up to 180. These are all things. When we came back right after break, the day we came back after break, are these all things I said everybody should know? Was that part of what we went over that day? Yeah. Stuff you gotta know. Alright? One of you is telling me, well, I don't remember having this in my notes. This is stuff you should know without having to look at your notes. Okay? On the homework, questions, problems you want to see worked off of page 306.
16.
16.
Oh, good, so it's okay.
Make sure you follow along. Make sure you understand this stuff. Stuff we do today, sort of some of the same ideas. A lot of new terms, a lot of stuff that you're probably going to be confused on just because it's so much new information. Problem 16, they give you a picture. My picture might not look spectacular, but it looks something like this. I'm not even going to write in all the letters. They say, is this an angle bisector? Ignore that stray part up there. Do we have enough information to say that that's an angle bisector?
Yes.
These two are congruent, but what else would have to be true?
They have to be right angles.
These down here would have to, that and that would have to be a right angle, so is that enough to say it's an angle bisector?
Stupid.
Yeah. No. So the answer would be no. And if you wrote down an explanation, the explanation would be no, because we don't know that they have the right angles going to the sides, or no, because we don't know that these are distances. Just because it goes from here to there, does that mean it's a distance? To be a distance, it would have to be a right angle. Next question. 20. Problem 20. I bet I ain't got no graph on here anywhere. I don't have a graph, but we'll do it this way anyway. This is one of them where we're writing the equation. This is probably one of the harder ones, and it's not really hard, it's just takes a little more work. -2, 0. That's point Q. 6, 12. Somewhere way up in here, somewhere like that. That's R. We're trying to write the equation of a line that's going to be the perpendicular bisector of that. So we want some line, and I'm just going to estimate here. We want some line that goes through this. Well, that looks way off. Goes through it. That's probably not any closer. Forms what kind of angles with that segment? Right angles, and it does what to the segment? Bisects it, splits it into two congruent. So we want the equation of that line. Anybody tell me anything before we start to write the equation of that line? Slope is going to be what? A negative, because it's going down, right? So when we do this, our slope better end up being a negative, otherwise we messed up somewhere. Can we sort of tell where these points are at? Where it's going to intersect? Yeah. Let's make a guess here. It looks like maybe about 1.6 maybe. Does that look about right? I don't know if that's anywhere close or not, but hopefully we're somewhere in that area when we find the midpoint. First thing said to graph it, what'd step 2 say to do from your notes last time? Find the midpoint, right? So we're going to take Q and R, and I laid my book down already. Somebody help me out. For Q and R, what are the x coordinates? -2, 0. So -2 minus 0, or I'm sorry, plus 0. Oh, that's the coordinates. Let's do this then so that we don't get confused. Let's write it down. What's Q? -2, 0. What's R? 6, 12. Now, looking at those two, now tell me what are the x coordinates? -2 plus 6 divided by 2. What's the y coordinates? 0 plus 12 divided by 2. Ignore those straight marks there. What's -2 plus 6? 4 divided by 2. So that's the x coordinate of the midpoint. 0 plus 12. 12 divided by 2 is, so that's our midpoint. Now we made a guess over here. Was our guess pretty close? Yeah, it was a little off. But what did the third step say to find? Slope. So we want to find the slope of this segment, the original. If I had a graph up here, I could just count rise, overrun. We can sort of do that. If we go from 0 up to 12, how much rise do we have? 12. Otherwise, you could use the formula to do it. If we go from -2 over to 6, how much over do we get? 8. Everybody agree with that? Somebody reduce that for me. You know your calculators will reduce it for you if you...
3 over 2.
3 over 2. Anybody agree with Harry? 3 over 2. We'll leave it as 3 over 2 because we want rise over run. What's step 4 say to do? Find the slope of the thing that's perpendicular to it, right? So what would that slope be? Opposite reciprocal. What's the opposite? That's supposed to be an M. -2 over 3. Just flip it over and change the sign. What's step 5 say to do? We use the y equals mx plus b. Stupid pen. We use these two, and we just plug in. What do we plug in for y? The y coordinate from right there. What do we plug in for m? -2/3. What do we plug in for x? 2. Now what do we do to find b? That's a b, not a 6 there, Jason. You can tell that, right? B. What do we do to find b?
You have to take that.
We have to
Multiply it by the m.
Multiply it here. So we get 2 times negative 2 is negative 4 divided by 3. It's not going to come out even, is it?
1.
So it's negative 1 and 1/3. That equals 6. Now what do we do? Everybody gets confused whenever you have these fractions, and it shouldn't be harder than with regular numbers. What do you do to get the b by itself?
You add the negative 1 1/3.
Add 1 and 1/3 to both sides. What's 6 plus 1 and 1/3?
7 1/3.
So b equals 7 and 1/3. That's our b. This was our m. Step 6 says to write the equation, you're just going to use y equals mx plus b. What do we put in place of m? The y stays the same, don't change it this time. What goes in place of m? Negative 2/3. What goes in place of b? 7 and 1/3. The only thing I might say about this to make it in a better algebraic form, change that to an improper fraction. If you're in algebra 2 next year, you wouldn't want to write it with 7 1/3 there. You'd want it to be an improper fraction. And to do that, all you do is take 7 times 3. What's 7 times 3? Plus 1. That's the best form. Either 2 forms would work though. I probably would have accepted if Jenna would have grabbed out her calculator when she got to this point and said, oh crap, I hate fractions. I don't like dealing with them. And she changed all these into a decimal form. Wouldn't have been a good decimal form, but I probably would have accepted the decimal answer also as she went through and did that. Next question. Don't make me turn it off. Next question.
34.
34. Is that the one with the streets? You better be paying attention while I'm doing this, Dawson. How many streets do we go on up and how many streets do we have going up and down? Nobody can count that many? Streets we got going up and down. Can't do it, Dawson. Nobody can figure out how many streets we got going up and down. 6. So 1, 2, 3, 4, 5, 6. Shh. How many streets we got going left and right? 5. 1, 2, 3, 4, 5. Gotta be following along here. I think I'm just gonna call on people since everybody's not following along. And I'm gonna ask you about a square. And you're gonna tell me if there's something in that square or not and tell me where it's at in that square. That's what I should do, right? Since people aren't following along. You got me, Dalton?
First, yes sir.
So is there anything in this first square?
Yes sir, there is.
Where at?
Hospital.
Where at?
Bloomingburg.
In that square,
Top
yeah.
right.
In the middle of the square.
Right in the middle?
Yeah, it's Mercy Hospital.
No, it's not.
It's in the
bottom
left corner.
Yeah, it's in the bottom left corner.
Bottom left corner.
Right there? Is that where it's at, Dalton?
Yes.
There's a little
Bottom, that's top left, yeah.
Bottom left?
Top left.
Bottom.
bottom left.
Bottom left.
Bottom left.
The box is yes, the top left. But
Is
there's
that
a
where it's
little-
at on the picture?
Yeah.
Right there.
Yeah. Oh yeah.
Now you know, okay? So now we got it straight, so now you're going to be able to explain it, right?
Yeah.
You said that's Mercy Hospital?
Yes sir.
So I'm just going to put M Hospital. M Hospital, that's right there. Anything in this box, Dalton?
Right.
No sir.
This one?
Nope. There's
Yeah.
Yeah, that's Trinity Hospital.
Where at?
Bottom
Right
right.
behind.
Bottom right or left?
Right.
Right?
In what, 4 blocks?
Trinity Hospital?
Yep.
Down one.
A, B,
Anything in this one? This one?
E3.
No?
Yeah.
No.
No.
Left
Sorry.
one. There you go.
Yeah.
Bottom right. Academy.
Academy School?
Next to the
Museum.
museum.
Is
Bottom
that-
right.
Bottom right, museum right there?
Yep.
Why are you writing so small?
Because I'm in those boxes, I can't do anything.
far right, there's none in.
This one?
Nope.
No.
There's none for.
No.
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 Yes. High Street
Left.
School, bottom left.
Bottom left? So H school, this one?
Nope. Nope.
No.
Yep.
Yes.
Roosevelt.
School, bottom left corner.
Bottom left?
Roosevelt School.
Our school.
No.
Yep.
Yes.
Wilson
Bottom left.
School. Wilson School.
Bottom left?
Yep.
Focused on.
Yes, sir.
You could be writing these down instead of sitting there doing nothing. Getting-
I was writing down.
I
Start writing
apologize.
this down.
So A, what's A ask us for?
Which school is
It's asking which school is
approximately
approximately equidistant from
Equidistant.
Equidistant.
from the hospital?
So from the two hospitals. The two hospitals are here and here. So we got a hospital there, hospital there. What point does it look like it's the same distance from both of those? What is it?
Our school.
The R school? Does everybody agree with that? That looks like it's about the same distance from there to there and there to there.
Closer.
And
So Roosevelt School. And we could figure that out sort of by doing like slope. What do I have to do to go from this school to that hospital? How would I move? Up 3 to the, over 2. If I go the other way, I go up 3 to the other way 3. Looks like it's probably the same, isn't it? B, what's B say?
Is the museum approximately equidistant from Wilson School and Roosevelt School?
So we're looking at the museum here. What two schools? Wilson
And Roosevelt.
and Roosevelt. Those two look like they're the same distances?
No, not really.
I don't look anything like they're the same distances. So what would your reasoning be there? How could you explain that reasoning?
Roosevelt's closer.
Give me a little more. Let's do, how do you have to go from the museum to the Roosevelt School?
Just go straight down.
Just go down 2, right?
Yeah.
Are we gonna get to this school over here if we just go down 2? No, so we gotta go down 2 and to the left 2. So most definitely that's gonna be farther if you can just, to go from one place to the other, if you can just go down 2, and then the other one you gotta go down 2 and to the left 2, is it most definitely gonna be farther? Yeah. You got more moving to do. And also, we could look at it, if you wanted to do it geometrically, what kind of shape do I have right there? Triangle, not just a triangle. What's true about this angle right here?
It's right.
It's a right triangle. What do you know about that side in a right triangle? It's the longest, isn't it? Side across from the right angle always has to be the longest. So if that side's the longest side, can it be the same length as this side?
Nope.
No. So if you wanted to explain it mathematically, that'd be another way you could do it. Other questions? All right, get those notes back out. You just want me to do your problems.
Yeah.
Get those notes back out. We're going to go over them. Before we go over those, I'm sorry, still set those off to the side. On a clean sheet of paper, you're going to start copying this down. I forgot that I added a couple things to this. So these notes, the notes that you grab back here, these notes that Jenna grabbed, and the notes you're getting ready to write down on this other sheet of paper, they go together as today's total notes. Does that make sense, Dawson? Can you handle that?
Yeah.
Got a clean sheet of paper?
In your seat.
Spectacular. Got something to write with?
No, I just want to see everybody look around.
We'll do it at the end if we have time. Wants to see everybody move around. That's exciting.
It is.
It's most
Kind of
time in
weird
this
if you
class.
ask me.
Funny. Well, you'll tell them about this.
So what we're going to cover today, medians of triangles, altitudes of triangles, perpendicular bisectors in triangles, and angle bisectors in triangles. And at some point I'll hang these up on the wall. These are my great things that I use here. I actually went through, and you're going to actually do this on the other sheet of paper when we get to it here in a minute. These are the three medians in this triangle. Every triangle is going to have three medians. Every triangle is going to have three altitudes. Every triangle is going to have three angle bisectors, so on, so on, so on. So we're going to draw these, and I'm going to explain to you what they mean. Just like a perpendicular bisector, when I tell you something's a median of a triangle, that tells you a whole lot of information. So you've got to be able to understand all that information. Other ones, angle bisectors. I bisected all three of these angles on this triangle. Notice that every one of these, when I draw it correctly, the angle bisectors, the medians, yes. Yes.
Sorry.
When I have these like this, you notice that all three of the segments all meet in the middle at a certain point. And that's what the next slide is going to tell you about, is what that point's called. You probably already figured it out by the other paper. Anybody know what that point, don't say centroid, any of the points where they all come together. When you're reading, when you were doing those notes.
Circumcentric.
That's a certain one. I want, anytime you guys are giving me specific names, I want the name.
Point of concurrency.
There you go. Point of concurrency. Those are the points of concurrency. Now this one's called a centroid because it's for medians. This one's called an incenter because it's for angle bisectors, and so on and so on. Circumcenter's one of the other ones, and we're going to talk about each of those. Anybody have a guess as to what a median is? Middle. Goes to the midpoint. All right? Anybody have a guess what an altitude is? Forms what? Right angles. All right? So when you're talking about altitude, what's the word altitude mean? Height. And that's what you're talking about when you're drawing an altitude, is the height. So if I just had some triangle and I wanted to find the height of that triangle, I would draw in something like this that forms a right angle. That's an altitude. It tells the height of the triangle. Do I need to go back?
Hey.
Ginger, you got to start watching. I bet he was sitting over there texting his mom, telling her to call the guidance office and get him called down there. He does stuff like that.
I don't know if I'd want this talk like doctor's school kind of discussion. It's like, it's a lot of notes. to get
Yeah, if you miss one day, you're done.
Time's over.
Hey, back off.
Look at that.
We were talking bad about it.
Yeah, probably.
Oh, we were.
Ain't no probably about it. You know, you walk out my room, I'm talking bad about it.
I know.
All right, concurrent. Concurrent means three or more lines that all intersect at the same point. That point where they intersect is called the point of concurrency. Point of concurrency. Something that's not real difficult, but it seems to confuse a lot of people. So I have my three lines here. These are my three lines. Where's the point of concurrency? Good answer. Doesn't have one. All right? If I have my three lines like this, now do they have a point of concurrency?
Right where you're.
Right there where all three of them come together. That's a point of concurrency. I'm looking at these fancy dancy triangles that I made, that right there is the point of concurrency for these three segments or these three lines, where they all come together. When we're getting ready to do this on your notes that you had, and we're going to draw in these pictures, I'm sorry, I switched, I didn't do it. When we draw in these pictures, guess what should happen when you draw in your segments or your lines here? They should all come to one certain point. Now you'll probably see as we go through this chapter, and I draw my three lines for some triangle. I might draw this line, then I draw this line, then I draw this line, and I do this. That's my point of concurrency. I have a big point because I can't draw very well. All right? You might have to go laugh, Harry, because you'll probably have to do it on your paper too when we're drawing it.
Wait, so do like the lights don't come from an angle, right?
It depends. We're going to talk about that in a minute. Inscribed and circumscribed shapes. This sort of confuses a lot of people because there's about 10 different ways you could say something's inscribed or something's circumscribed. On this picture, you say that the triangle is inscribed in the circle. So the triangle's inscribed in the circle. Because the triangle's on the inside, the circle's going around the outside. Now to be inscribed, a shape has to have all its vertices, all its corners on the circle. So if I had a shape like this and had this four-sided figure, is it inscribed in that circle?
No.
No, because this corner doesn't touch it. All right? Now the other thing that could happen is you could have something like this. Now the triangle's not inscribed in the circle. Anybody have a guess how we would explain this picture? The circle is what? Inscribed in the triangle. So we could say it that way. Now, some of you pointed out this bottom one. That says it a completely different way, doesn't it? Because now instead of using inscribed, it uses what? Circumscribed. So if we're going to start off with the word inscribed, we talk about the shape that's inside. If we're going to start off with circumscribed, we talk about the shape that's outside. So circumscribed means the shape's going around the outside of the other shape, whatever it is. Inscribed, right, for circumference. And inscribed, inside, means the shape's going are on the inside of it. When you circumscribe something, the circle has to touch all three sides of the shape, whatever it is. So, if I had a rectangle, somebody want to come up and try to circumscribe or inscribe a circle in that rectangle? It's not possible. How come it's not possible?
Because you can't touch all sides.
You can't touch all the sides if it's a circle. If I tried to touch all sides, it would no longer be a circle. It would draw. It would be an ellipse. Alright, so some shapes can be inscribed, some circumscribed, others might not be, it might not work out. So inscribed, again, you talk about the shape on the inside first. Circumscribed, you're talking about the shape going around the outside. So here we'd say the triangle is circumscribed about the circle. Here we would say the triangle was inscribed in the circle. Or we could change this one and say the circle is circumscribed about the triangle. Talking about the one on the outside first. All right, what I need you to do, go back here on the back table where you turned in your quiz and stuff and you grab the notes. Grab 3 things on top of that one box right there behind Izzy. Protractor, ruler, and a note card. Protractor, ruler, and a note card. There, Dalton, the wish came true. You get to see people move. I'm not sure why that's...
You're weird.
Yes.
Yes.
I'm not weirdo, I just want everybody to move around. It's not like walking around. This is weird. Where's the note card?
Right there. What did you say?
Huh?
I don't know. You stole my note.
I don't think so.
You're like the second
One person walking around.
You listen to him. I sort of ignore.
Look at you. Man, I got like,
Let's go quick because we're going to run out of time, and regardless, we're still going to have the same assignment. 11:47. Could have looked right over there.
I don't know how to read over. They're like, I can't by themselves. I can't read.
Ethan probably get himself a new gift.
First, what we're going to do, set that stuff off to the side. We're going to use it here in a second. Get out the notes that you picked up from back here. We're going to fill in, starting with the median. Median. First thing, next to median, you're going to write the definition. Definition of a median is a segment that runs from
Ran this on what?
the vertex of a triangle to the midpoint of the opposite side. So as you're writing that, if I tell you that this segment right here is a median, starts at up one of the corners, and it goes down here and it intersects this opposite side at the what? Midpoint. All right? This one starts at this corner, goes to the opposite side, intersects it at the midpoint. So what can you tell me about these two segments right here? They got to be congruent. How about these two segments right here? They got to be congruent. How about these two right here? They got to be congruent. All right? So that's what a median does. What's the next thing under median say? Point of concurrency. Point of concurrency. I'm not going to write this out every time because it's there on your paper, right? Point of concurrency, where all the three medians come together. That point of concurrency where they all come together, it's on this paper. And this paper again will be hung on the wall here soon. It's called the centroid. You got to know that when you see the word medians, you're going to think of centroid. When you see centroid, you're going to think of medians. When you see centroid, you're also going to think of midpoints. All three of those words got to go together. You got to start putting them together in your head and say, okay, if they tell me I have a centroid, if I tell you that this is a centroid, then what can you tell me about these two segments down here? They got to be congruent because this has to be a midpoint, that has to be a median, so those two segments have to be congruent. What's the next part say on it? Centroid theorem. Anybody find the centroid theorem?
I got you.
Somebody tell me what it says.
The centroid of a triangle. The centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side.
Now, what you might want to do on this one, I got to remember how I explain this. I need my notes so I don't tell you wrong. On the centroid theorem, what it says, read it to me one more time. We'll write it down this way. Then you've got to listen closely so you understand this. Centroid does what? Centroid of a triangle
Is 2/3 of the distance from each vertex to the midpoint of the opposite side.
Now you've got to listen carefully. You're not going to understand this, and this is probably the most important thing that we've covered so far today. This is the thing that we're going to do the most with. It's 2/3 of the distance
From each vertex
from vertex
to the midpoint
to midpoint
of the opposite side.
of the opposite side. And I'm not going to write all that out just because we know if it's a median, then it's got to go from a vertex to the midpoint of the opposite side, right? What that means, if I'm looking at my triangle right here, this is my triangle, and I'm looking at it, this distance from here to there is 2/3 of the entire distance. All right? So if this is 2/3 of the distance, what's this part? 1/3. You can use it that way and know that this is 2/3 and this is 1/3. You might want to draw your little picture there and say, you know, if that's your centroid, that's 2/3 of the whole distance. That's 1/3 of the distance. The other thing that I want you to write down there, this is the part I had to look up to try to remember how I want to explain it to you, is I want you to write it down this way. Vertex to centroid is twice centroid to midpoint. And I know this sounds confusing, but it's not as hard as it seems to be. If I have this triangle and I tell you that's a median, and that's our centroid right there, and I tell you this over here is, let's say this part down here at the bottom is 4, how long is this part up top going to be? 8. All you do, these two parts, that should be an 8. This part is twice as much as that part. So this part right here has to be twice as long as that part. So if I'm looking at this and I told you this right here from this point to that point was 10, how long would this point, the centroid to the vertex be? 20. Now we can also go backwards of that. If I tell you that this part from here to there is 50, how long is this part where my two fingers are touching? 25. That's what it's saying. From the centroid to the vertex is always twice as long as the centroid to the midpoint. Now the other thing that you could do with that, and that's what the original theorem goes off of, is what if I told you this whole thing right here was 30? Could we find the two parts? All you do if the whole thing is 30, you take 2/3 times 30, and you take 1/3 times 30. You have your calculator and you do 2/3 times 30, what do you end up with? 20. 1/3 times 30? 10. So this part's 20, this part would be 10. If they tell you the whole thing, then you use that. If you use your calculator and you punch in 2 divided by 3 times 30, it'll give you the whole number answer. It'll do all of it for you, and you won't have to worry about keeping track of the decimals and all that. That sort of make any sense? Jen, did that make any sense? Are you lying to me just so I'll quit talking to you? I think she is. Next thing we're going to do, we're actually going to draw these medians and centroids and stuff on this. So you're going to take your ruler and you're going to measure each side. Measure each side, and then you're going to find what for each side? What do we want on each side? The what? For the side. Midpoint. So just find the midpoint of each side on all 3 triangles. Find the midpoint. I'm just going to guess. That looks like a midpoint. That looks like a midpoint. That looks like a midpoint. This one, that looks like a midpoint. And for that side, that looks like a midpoint. That looks like a midpoint. Midpoint. So you should have a point on each side of your triangle, all 3 triangles when you're done. Right in the middle, the midpoint. Boy, that one's way off. Oh well. Hopefully yours is better than mine. Doesn't have to be exact. Again, whose notes are these? Yours. So just find the midpoint of each side. Harry's up here and he's measuring to beat everything. He's trying to get exact. Don't have to be exact. Find the midpoint. Something close. Now look at Ethan, and he's already given up on measuring. He's just estimating where that midpoint's at because he got tired of measuring. Once I have the midpoints, is everybody getting pretty close having all the midpoints? How many midpoints should you have? 3 for each triangle, so a total of 9. Once you have that, what I want you to do is take your ruler. You're going to connect the corner, the vertex, to the midpoint that's on the opposite side. So you're just going to do something like that. What's that segment called? Median. Do it for the other one. Median. Do it for this one. Median. What's that point called right there in the middle? Centroid. Do that for all 3 triangles. What should happen when you draw all those 3 segments in there? Every time they should all cross somewhere at one point, right? Get done drawing all those. I want you to write this somewhere in that area there. What did you notice about all three centroids? They fall where? Inside the triangle somewhere. Centroids are always going to fall inside the triangle. No matter what kind of triangle I draw, the centroid's going to be inside the triangle all the time. Now, I don't want to say the middle of the triangle, because if I ask Peyton to come up and tell me where the middle of this triangle is he probably going to point right to there? Oh no, that's sort of hard to find the middle of a triangle, isn't it? This one here, this looks more like, maybe that's the middle. You might even go up here a little bit and say, oh, that's the middle. So it's sort of hard to find the center or the middle of a triangle. So that's centroid. Got that?
Yep.
All centroids fall inside the triangle, always. They always fall inside the triangle. Everybody getting pretty close? Going to the next one. Altitudes. Somebody give me the definition of an altitude. Sort of. Anybody find it in the book, see what it said? Nobody could find it? All right, so I'm going to give you... Do what? That might go along with the altitude. That's the point of concurrency. Perpendicular segment that runs from vertex of a triangle to the opposite side. So it starts at one of the corners of the triangle and it runs to the opposite side. And I'm even going to put a little extra here. What perpendicular tell us? That it does what? Forms right angles. Forms a right angle. We said that when we said perpendicular, but so altitudes. Altitudes look like this. And this just happened to be the triangle that I drew. It doesn't always have to look like this. But for this triangle, this is what it looks like. It goes from a corner down to the opposite side, and it forms what with that opposite side?
Right.
Right angle. Goes from this corner to the opposite side, and it forms a right angle. This corner to the opposite side forms a right angle. They all meet here at one certain spot. That's the point of concurrency again. What's that point of concurrency called? Orthocenter. So you want to write that in there on your blank where it says the point of concurrency. Orthocenter. So when you hear orthodontist, you think of birds.
in your mouth.
The birds are in your mouth. Is that?
Wait, so it's the two birds and not
What's the next thing on there? So have a.
Make a conjecture as to the location.
All right, we're going to do that here in a second. It didn't have a theorem, did it? Orthocenter didn't have a theorem, so we don't have a theorem for orthocenter. So we don't have to worry about that. Next thing we're going to do is we're going to draw them on here. To draw these, this is where you're going to. This is where you're going to take your note card that you grabbed back here. All right? Mine's too big for a note card. All you're going to do, you're going to lay your note card on one of the sides of the triangle. I got to find one where it'll actually work. I'm going to lay it on this side. What do I know about that angle right there?
Right.
It's a right angle. So I'm going to lay it on that side and I'm going to draw this. So use that note card so that it forms a Right angle right there.
You had to do that one?
Yeah. It's not on there?
No, I'm saying, do we have to do that triangle, or do you want us to do?
Oh, go ahead and do them all. So, I don't have something that's big enough to lay on my triangle to show you here, I don't think.
The ruler.
I could just use a ruler if I wanted to use something that looked like your note card. I found the book. So this is your note card. I'm going to lay it on that vertex, or I'm going to lay it on this side down here. Make sure it matches up with the side, match it up with the vertex. Draw this in. It's going to form a right angle right there. Do the next side, go over here, match it up with that side. Bring it over to hit a vertex, hit this vertex over here. Wow. I should not try to use that book, I don't guess. It's going to come over here, forms a right angle there. Same thing here, comes over, forms a right angle. That point right there, what's that point called again? Orthocenter. Orthocenter. You can use your note card to make sure you're making a right angle. Goes from a corner to the opposite side that forms a right angle. So every time you hear altitude, what are some other words you should think of?
Right.
Right angle. 90 degrees.
Can you do like the right angle as well?
You want me to do the bottom?
Yeah.
Let me do this one real quick, and then, so from here, from this side, from this over to there, I'm going to do both these. Everybody get the first one?
Yeah.
That one, that altitude's pretty easy. The other altitudes are sort of confusing. What kind of triangle is this triangle?
Right triangle.
A right triangle. So if I want to make a right angle from this vertex to this side of that triangle, how's it going to go?
Straight down. It's already got it.
It's one of the sides of the triangle, isn't it? From this one, how's it going to go?
Right. Right.
The other side of the triangle. If it happens to be a right triangle, then two sides are also altitudes. Two of the sides are also altitudes if it's a right triangle. Does that make sense? Jason, that make any sense? This side and that side are going to be altitudes to the triangle too. That's why when you were doing triangles, when you were finding area of triangles back in like 4th or 5th grade, and they told you 1/2 times base times height, and the height was the altitude. Well, if they gave you a right triangle and they told you this side over here was 8, that was your height. Okay? So they didn't have to give you a height there because that is an altitude. That is the height of the triangle. On this one, everybody's confused on this one. First, let's go back to this one. Where's the orthocenter at?
Right in the middle of the line.
That right there is your orthocenter. Might want to write that down. That's your orthocenter. Right there at the corner of the right angle is where they all three come together. This one, pretty easy to draw that, altitude. Now when I want to go from this vertex to this side, can it go like that? Is that going to form a right angle?
No.
How about that? About that? What needs to happen?
That's it.
Extended.
You have to extend it out. You're going to extend this side out. So you extend this side out, and then what do we do with it? Drop it straight down there, form a right angle. What do we do with this vertex over here? We're trying to get to this side. You got to extend it out. I can't extend it out on mine because it's going to end up being down here below my board somewhere. Where's the orthocenter going to be on this one? Where's the orthocenter at? Is it inside the triangle? Is it on the corner, one of the corners of the triangle? The orthocenter is somewhere outside the triangle. So for an obtuse triangle, the orthocenter falls somewhere outside the triangle. Mine, I take my three things here, see if I can hold all three of them. Mine's gonna be like way down here somewhere. That makes sense on your paper? So the ortho center here is outside, ortho hip center here is in the center of the triangle, or inside the triangle. The ortho center for a right triangle is on the edge of the triangle. Perpendicular bisectors. What's a perpendicular bisector? We had this last time. Right, and for perpendicular bisectors of a triangle, forms right angles. So it's going to form right angles. Forms right angle. And bisects side of triangle. Now, something you want to write down on this one somewhere on your paper. Does not have to start at a vertex. All the other three have to start at one of the corners. The perpendicular bisector can start anywhere. Notice on mine here, this perpendicular bisector starts right here. Goes over, hits the midpoint, and forms a right angle. This perpendicular bisector starts right here, goes down here, hits the midpoint. Those two are congruent, forms a right angle. This one starts right here, goes out that way. So perpendicular bisector doesn't have to start at a corner. That's the only one of the four things that we're covering today that doesn't have to start at a corner. All the rest of them will start at some corner of the triangle, the vertex, and run somehow. Perpendicular bisector doesn't have to. What's the point of concurrency for a perpendicular bisector? What is it? Circumcenter. So make sure you write that in. Circumcenter. Circumcenter. Does it have a theorem? It does. What theorem does it say it is? Circumcenter theorem? Did anybody find the circumcenter theorem? Circumcenter.
Of the triangle is equidistant from the vertices of the triangle.
Circumcenter is equidistance
From the vertices of the triangle.
from the, and I'm going to write it a little different. Instead of saying vertices, I'm going to say from the three corners of the triangle. Everybody knows that a corner of a triangle is called a vertex, right? It's vertices. So circumcenter is equidistance from the three corners of a triangle. Equidistance from the three corners of a triangle. Everybody sort of have that? I'm going to go to the next one so I can explain something real quick. We're not going to draw the next one because I want to get on to angle bisector. So if I'm drawing the perpendicular bisectors, however they work out, and I didn't really need to do this, I should have just used this since I have the perpendicular bisectors here. What it's saying, right here is our circumcenter. This is where these three happen to concur with each other, meet. The distance, from my fingers here to this corner is the same as the distance from my fingers here to that corner and my fingers here to that corner. All three of those distances are the same. So if I told you that this point, I'm going to make up a point here for the perpendicular for the circumcenter. I'm going to say that this right here is the circumcenter. The distance from that circumcenter to there, distance from the circumcenter to there, and the distance from the circumcenter to there, always all three have to be the same. So if this one was right here, if that's the circumcenter, that distance, and that distance are always the same. That's what that theorem says. That's actually an easier theorem than the median theorem, but it's more confusing because you don't actually see that.
Got where I put them.
Real quickly, next one. Angle bisectors. What's an angle bisector?
Into two congruent angles.
Splits angle into two congruent angles. Point of concurrency for an angle bisector, what is it? In center? Is that what it is? In center? What's that tell you about it? Where's the in center always going to be? It's always going to be inside the triangle. It's always going to be inside the triangle. So it's not going to fall outside or on the triangle. It's always going to be inside. Did it have a theorem?
Yeah.
What did the theorem say? Was it called the in center theorem?
Yeah.
In center theorem. What's it say? Nobody found it?
Oh, the center of a triangle is equidistant from the sides of the triangle.
In center of a triangle is the same distance, equidistance. Don't go anywhere yet. Same distance from all three sides. So it's the same distance from all three sides. That's the in center theorem. Sort of like the last one that we just did. And this. Find it in the book there, you'll find it. That's your assignment. I'll do something with this next time since I know that we sort of did get over everything that we could have maybe. Lay it on my chair. Pass these papers around and grab your paper. That was my fault. I didn't mean to throw it at you. This is the paper that you did last time. You're welcome.
Is where it crosses the
I was
intersection.
Median, what's it do?
A point of currency of a median of a
We don't want the point of concurrency, we want the definition. So if you don't have this, write this down the way I write it, because I'm going to give you the best explanation that you can have. Easiest. Segment
Point of the opposite.
that runs from a vertex of a triangle to the midpoint of the opposite side. Now, as we're writing these notes, if you don't have this stuff all filled in by the time we're done, do you think when I collect your binder, I'm giving you credit for me typing all this out for you? Probably not. So if I drew some triangle here, doesn't matter what the triangle looks like. This is what a median is. Median starts at some vertex, so I'm going to pick that vertex. Vertex is just a corner, right? Anytime I say vertex the rest of the day, if Braden wants to write down corner instead of vertex, because he's going to know what that means better, write it down. I don't care. Whatever helps you out. So we started at a corner. We want to go to the midpoint of the opposite side. I'm going to guess that the midpoint of that opposite side is about there. That segment, going from that vertex, from that corner to that midpoint, is called a median. That's a median.
Are we supposed to be writing this down with this paper or?
Yeah.
That's fine.
Yeah. Just filling in all the stuff.
Just making sure.
Next, and I'm going to use this so I don't have to write it out every time. POC. What do you think POC stands for?
Point of currency.
Point of concurrency. So I don't have to write out point of concurrency every time. That's the next blank on your thing there, right? What is the point of concurrency of all the medians of a triangle?
Current lines.
What is it? Centroid. So put that in that blank. Centroid. It's called the centroid.
Like the point of concurrency of the median of the triangle is called the
Centroid.
Dang, I had the wrong thing.
Centroid. So I have this triangle. I've drawn this triangle a couple years ago so I could have it every time. I go from this vertex to this midpoint right down here. So what do I know about these two segments right here?
They're congruent.
They're congruent to each other. Good. They're congruent. That segment is called a median. I go from here over to here. That segment is called a median. I go from here over to this vertex. That is called a median. Notice that when I draw all three of those, they meet at one exact point. Every single time, no matter what the triangle is, those three are going to meet at one certain point every single time. Does everybody understand that? Because here in a few minutes, you're going to be filling in your pictures up there. The next thing, I think it was called the centroid theorem, right?
Yeah.
Centroid theorem. Somebody tell me what the centroid theorem says.
The centroid theorem of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side.
Centroid is 2/3 of the distance from 2/3 of the distance from the what?
From each vertex to the midpoint.
From the vertex to midpoint of opposite side. And I'm going to abbreviate opposite OPP, all right? Opposite side. Now I write that down, and if I wasn't paying any attention, it confused the heck out of it. Because hardly anybody understands the way that theorem's worded. All right? So I am going to tell you another way to write that theorem down. And this is, I want you to write this down somewhere on your paper there. Before I do that, I'm going to try to erase this stupid extra line that I got going through there so it doesn't look like anything.
The book said to write it down the circumcenter of a triangle.
We're not circumcenter, we're on what?
Centroid.
Centroid.
Oh. But it said the
I know, we haven't got to circumcenter yet. We're on centroid. Centroid goes with medians. These two go together. Circumcenter doesn't have anything to do with either one of these two. You're looking at the wrong thing. Circumcenter goes with one of the other ones that we're going to cover here in a little while.
Okay, so we're on centroid.
We're on medians and centroid theorem.
And we're,
I'm getting ready to tell you another way to write it down there on your paper for centroid theorem. Centroid theorem, better way to say it, the centroid to vertex of a triangle is twice the centroid to midpoint. And I know that might not make a whole lot of sense, but I'm hoping when I explain it here in a second, it'll go. Does that make any more sense? No?
I don't know.
Simplify a little bit.
My brain isn't really
Makes sense.
working anymore.
So, if I'm looking at, that's the midpoint, right? That's the centroid, that's the vertex. If I'm looking at it, let's do the top one because I can't hold it, well, maybe I can turn it around this way and hold the triangle and it'll stay. So we have that. The theorem says this distance from the centroid to the vertex to the corner is 2/3 of the whole distance. All right? So if this is 2/3 of the whole distance, this part over here is what? 1/3. That confuses people because you stick those fractions in there. The way I've got it stated down there is to say that the distance from here to there
It's twice as long as the other
is
side.
twice as long as this one. So if I told you this one over here, this distance was 7.
Means the other side's 14.
This side over here is
14.
14.
Okay, that makes sense.
All right? Now, when you're going to use their rendition of it, their version of it, is when I tell you this whole thing from here to there. Let's say I tell you that whole median is 30. Can you find the distance from here to there? The way you do it is you take, for their version, they say it's 2/3 and you told me the other part is 1/3. So if I have this triangle, and this is my centroid, boy, that's a horrible, horrible picture. If I have this triangle, this part is 2/3 of the whole distance. This part right here is 1/3. All you do, if you know that whole thing is 30, is you take 2/3 times 30. Every one of you is supposed to bring a calculator every day, right? So what is 2/3 times 30? 20. If you punch that right into your calculator, it'll do it for you. What's 1/3 times 30? 10. So if I told you this whole thing was 30, how long is this part? 20. How long is this part? 10. That's what the theorem's telling me. What if I told you that this part right here, from this corner to the centroid, what if I told you it was 50? How long is this part from here to there going to be? 25. It's going to be half of that, right? So you've got to know which way you're going. Caleb, that make any sense? You sure? Don't lie to me. So that's the centroid theorem. I would do something over to the side or maybe circle all these. Anytime you hear the word median, what's something else you're going to think of? Centroid. What's something else you're going to think of? Midpoint. All right? Those three things got to go together. Anytime you hear median, centroid. Anytime you hear centroid, median. You got to know that when you hear one of those, you're probably dealing with the other ones also. Next one, or no, I'm sorry, not the next one. What we're going to do. What we're going to do on your paper there, you're going to take your ruler and you're going to draw the medians for all three of these triangles on your paper. I look at Gavin's, he's already got it. Now, you could take your ruler and measure every one of these. I wouldn't try to be real precise. Mine looks like it's about 56. So what's half of 56?
28.
28. So I'm going to be somewhere about there. You can do that with your ruler. I'm going to sort of estimate mine up here. Just fine for now. Just find the midpoint of all the sides in all three triangles. So put a point about where the midpoint is. We don't want to take 10 years to do this. Those look like they're the midpoints on this one. Midpoint might be right about there. Midpoint about here. Midpoint about there. This one, midpoint's about here. Midpoint about there. Midpoint's about there. So find all three midpoints. Find the midpoint of each side. Owen's going to start listening to what I'm telling him, and he's going to find the midpoint before he starts drawing these in. Find the midpoint of the three sides. Then we're going to connect that corner right there to that midpoint, right? That way, and do that on the other triangle so that you can, then once you have that, then you can connect it. So I'm going to connect this vertex to that midpoint right there. What's that segment called? It's a median. I'm going to connect this vertex to that midpoint. What's that segment called? Median. I'm going to connect this one to that. What's that segment called? Median. What's that point right there where they all came together called? Centroid. That's your centroid right there. Do that on all three triangles. Connect the vertex to the midpoint, vertex to the midpoint, vertex to the midpoint. That's horrible. As long as you can understand it, that's all that's going to matter. Now, as you're doing this, somebody help me out. If I told you this segment right here was 18, how long is this segment right here? 9. If I told you that this whole segment from here to there, that whole median right there, if I told you that whole thing was 27, how long is this part? 18. How long is this part? 9. Remember, you take 27 times 2/3, 27 times 1/3, and it'll tell you. Or, the way I like to do it, I just like to say, okay, is this number divisible by 3, and split it up into 2 parts and compared to 1 part. Does everybody's picture look like those? We ready to move along? Centroid. Centroid theorem, very important. Every time you hear the word centroid, what other 2 words should you think of?
Outside.
Centroid goes with what? Median, maybe vertex, midpoint. All right? Make sure. Next one. Altitudes. Somebody help me out. Altitude of a triangle.
It's the height of it.
So I'm going to write it this way. Segment that runs from vertex or corner, if you want to write corner, of a triangle to opposite side. And once it gets to that opposite side, what's it do? Forms what? Forms what kind of angles?
Right angle.
Right angles. Forms right angle. Forms a right angle. So if I have my triangle here, if that's my triangle, I want to go from this vertex. I want to draw an altitude. Am I going to draw something that looks like that? I want it to go from this vertex to this opposite side, and I want it to make a what?
So it has to be perpendicular.
It's got to be perpendicular. It's got to go down there and form a right angle. Now, they give you more than that on the definition because, and let's go back. I'm going to go back to this. Something I want you to write down for medians. Somewhere in that medians part, what did you notice about all the centroids? Where did they fall? They're in the triangle, right? So write that down. Centroid is always inside triangle.
Where was that at?
It's just anywhere close to median, up in here, like there or something. Centroid is always inside the triangle. Wyatt asked me a question about how to answer that one question on there, and Paige was asking the same question. That's what they want. They want to know, hey, where does that fall at? Well, for a centroid must always be inside the triangle. No matter what kind of triangle it is, it's got to be inside. Centroid always has to be inside the triangle. So we had the definition up there and I erased it. Point of concurrency for altitudes. What's the point of concurrency for altitudes? Ortho-centered. Ortho-centered. That's the point of concurrency for altitudes. Ortho-centered. So make sure you got ortho-centered written in that blank. The theorem. Is there a theorem for altitudes? There wasn't one, was there? But what I am going to do, so orthocenters, everybody got orthocenter? Every time you hear the word orthocenter, what should you think of? Altitudes. And what kind of angles? Right angles. You think of those three things. You hear one of them, you should think of the others. Altitudes, right angles, orthocenter. I'm going to do this real quick. I'm going to draw this triangle up here so I can actually show you. One of the triangles that you have to draw the altitude to looks something like that, right? Does that look the same except for the little stray mark?
Yeah.
We're going to draw all three of them here in a second, but I want to do this one first. To do this, what we have to do, we're going to go from that vertex to the opposite side, and we want it to form a what? Right angle. The reason you have that note card there is because you're going to take this note card and you're going to use it because what do you know about that angle right there? It's a right angle. That way you don't have to measure. Right? I don't have a note card like that that's big enough, so I'm going to try to use this piece of paper. This is the way you're going to do it. You're going to line up the edge of the piece of paper with the opposite side and then move it over a little bit until you can draw right along that straight edge. That's going to form a right angle right there. That's an altitude. That's an altitude. Do what? No, for the three triangles. So the one I'm on right now is that one right there. So you draw that in there. What? No, you already have it down there. So just fix it. Oh, what'd you do? Draw it on the wrong triangles. So just know in your notes, tell yourself, hey, I got to switch these. These two are in the wrong. You can handle that. I have faith in you, Brady. What, people having faith in you?
No.
I want to make a right angle from this vertex. This is where you guys are going to have trouble, so watch closely. If I draw that right across there, is that going to form a right angle with the opposite side? How about there? 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 There?
It's not going to be on the triangle, it has to be off the triangle.
To make a right angle, it's going to have to be out here somewhere, right? So what do we got to do with this side? You got to extend it out. So what you're going to do is extend that out. And then you're going to draw in your altitude out here. It's going to form a right angle. So you're going to extend that side out. If I go to the other vertex, Dalton, any of this sinking in through that thing you got on your shoulders? Apparently not. If I want to draw it to that side, you got to extend it out. So it's going to be extended out like this somewhere. All right? Looks like maybe about right there. Does that look like that's going to be a right angle? Pretty close. Now the bad thing is, the three of them should come together because that's where the orthocenter is going to be. Where are my three going to come together at?
Somewhere.
Somewhere like down in here, right?
Yep.
So where is the orthocenter for this triangle? It's outside the triangle. The orthocenter ends up being outside the triangle. So you might write that down. Orthocenter for this triangle, what kind of triangle is that? It's an obtuse triangle. So for an obtuse triangle, orthocenter is outside. It's outside the triangle. For an obtuse triangle, the orthocenter is going to be outside. I'm going to go to this one. If I draw the altitudes for this one, from here to there, form a right angle, you can use your card on this one, right? Just make it come down here and form a right angle. Use the corner of your card. Mine's going to look something like that. From this one, use your card, line it up with that side, go over here. It's going to come over there, form a right angle. From that one, over to there, it's going to form a right angle. Where's the orthocenter on that triangle? It's inside. So the orthocenter, does anybody know what kind of triangle that one is? It's an equilateral. Give me a different name. Equiangular. Give me a different name. It's an acute triangle. For an acute triangle, the orthocenter is always going to be inside the triangle. It's always going to be inside. What kind of triangle is this one? It's a right triangle. Right triangle. Anybody have a guess where the orthocenter is going to be? If I draw this, the first one, if I go from this corner and go over there, that's going to be that altitude, right? So that is easy enough because it's inside like normal. But then when I go to this one, the opposite side is this side right here. Caleb takes his little note card and he does this, lines up the opposite side down here. And where's the side, where's the altitude going to be drawn at? Right on that side. If we do it from this one, where's the altitude going to be drawn at? Right on that side. So if it happens to be a right triangle, if that's a right angle right there, where's the orthocenter? The orthocenter is right there at that vertex. Now, what Paige and Wyatt was asking earlier about that question at the bottom, where it says what? Make a conjecture as to the location. Where can the orthocenter of a triangle be? Could be inside, could be outside, it could be on. The orthocenter could be anywhere. So that's the conjecture that they were asking you. Where is it at? Could be any of those places. Where did the centroid have to be?
Centroid has to be on the underside.
Has to be inside, right? Has to be inside. Centroid's always going to be inside the triangle. Orthocenter might be outside. I'm going to hang these up here in the next couple of days. So that way Owen, because he's a smart young man, when I hang it up over there and we take a test over this, and he goes, "Dang, I don't remember what orthocenter means." Can he figure it out real quick? Yeah, orthocenter goes with what? The altitude. So what do we know about when it goes from that vertex over this side? What's it going to form?
A right angle.
A right angle. Next one. I think you got to flip your paper over, don't you?
Yeah.
Next one, angle bisectors, or I'm sorry, perpendicular bisectors of a triangle. Is that the next one?
Yeah.
First thing I want you to write down somewhere in the space there for perpendicular bisectors. All three of the other ones have to start at a corner of the triangle. This one starts wherever. Does not have to start at a vertex. Does not have to start at a corner.
That's for like the definition.
Now that's just something I'm just telling you.
Is that for angle bisector of the triangle too?
No.
It's just for
Perpendicular bisectors is only one for. So if I'm looking at this is my perpendicular bisectors. My triangle got for up here. Notice that this perpendicular bisector starts here. That's not a corner of the triangle. And it runs to there. That's not a corner of the triangle. It's just some random segment going through there that is perpendicular to this side of the triangle. And what else does it do to that side of the triangle? Splits it into two equal parts. It bisects it. So what do I know about this segment and this segment? They got to be congruent. Going for this one, perpendicular to this side of the triangle, and it splits it into two congruent segments. Notice again, are they running from the vertices? No, they're not running from the corners. All three of the other ones that we're going to cover today start at a corner and go to an opposite side. Perpendicular bisector doesn't. Now, give me the definition of a perpendicular bisector.
Is it like an orthocenter that can start anywhere in the triangle?
Just give me the definition of perpendicular bisector then. What did we say last time? What's it do?
Let's say line to two sides and form right angle.
Splits a side of triangle into, sorry, I started writing cursive, two congruent segments. And what else does it do? And forms a right angle. So if I have this triangle and I want the perpendicular bisector of this bottom segment, I find the midpoint, and then I want some line or some segment that runs through that point that's going to form a right angle. Well, is it going to go like that? Is that going to form a right angle? No, it's going to be something that runs right like that. So it's going to form a right angle, and it's going to make these two congruent. Notice, does that one run to any place special? No. So it's just got to be it's a random line in there somewhere. Next, point of concurrency for perpendicular bisectors. Circumcenter. Everybody agree with that? Let Owen get his little chuckle out of the way. You got your chuckle done? Oh, you didn't chuckle this time. You did. I know you chuckled the first time when we said circumcenter. Or no, that was circumscribed, wasn't it? I'm sorry. Yeah, I shouldn't even have brought it up, should I? Does this one have a theorem? Circumcenter have a theorem? Give me a second. I'm going to erase some of this because I don't really want this. I didn't mean to erase all of it. Oh well. Circumcenter theorem. Circumcenter. Give me a second to write this down. Circumcenter theorem. Should have this. Circumcenter theorem is more difficult than the centroid theorems. Lost my train of thought. It's more difficult. Once I explained that was pretty easy, right? This part's twice as long as that part. Nothing hard about it. Circumcenter theorem's a little harder. What's it say? Now tell me.
The circumcenter of a triangle is equidistant.
Circumcenter of a triangle, and I'm not going to write equidistance because that's too much for me to write, and I don't know how to spell it. Is same distance from the vertices. What's another name for the vertices? Give me something else easier. If I draw this triangle, what is that right there? It's corner, right? So I'm just going to say corner. It's the same distance from the three corners of a triangle. I'm spelling like Dalton over there now. So, this point right here is the circumcenter for this triangle. What that theorem is saying is the distance from this point to this corner up here, the distance from that point to this corner right here, and the distance from this point to that corner right there, guess what has to be true about all three of them? They're all the same. So if I drew a triangle like this, and I told you that point right there was the circumcenter, that's the circumcenter of this triangle. What do we know about the distance from there to there, there to there, and there to there? They're all three the same distance. Now, that's sort of hard to understand when you're looking at this triangle, because do we have those three distances drawn in the triangle? Do we know the distance from here to that corner? It's not even one of the segments that we drew when we drew all the perpendicular bisectors. All right? So when you see something like this, you're going to have a triangle, and it's going to have all the perpendicular bisectors in here. They're going to look like that, and that's going to be the circumcenter. Then there's going to be these extra lines in here, or extra segments in here, something like this. And what do I know about those three segments? They're all the same. They're all the same. But if you look at that triangle, it gets real confusing real quick. So all three of those have to be the same length. All three of those distances. What is your question, Owen? Got it? So perpendicular bisectors. We're going to skip over drawing these. Well, let's do the first one, then we'll go on. No, let's not do the first one. I don't like the first one. Let's do the last one down here. I want the perpendicular bisector of this triangle. First thing I'm going to find is I'm going to find the midpoint. So I'm going to find the midpoint of this side. Tell me to stop about when I'm at the midpoint. Past it? Right there? Is that all right?
Yeah. Sure. It's good enough.
Now, we want to go through that. We want some segment that goes through that, but it's also got to form a what? Right angle. Where's your note card? So I'm going to take this, and I'm going to do this. Line up the bottom. That forms a right angle right there. Do that right? I think so. That's the perpendicular bisector. I do the same thing over here. Find the midpoint somewhere about there. This one's going to go straight up like that. Sorry, I've got that straight line going outside. That's the perpendicular bisector. This one, the midpoint over here, somewhere about there. You want to form a right angle. That's a perpendicular bisector. That's not a very good one. Where's the, what was it called? Orthocenter, is that right? Circumcenter. Oh, circumcenter. Where's the circumcenter going to fall for this triangle? If I extend those out, if I could draw it all straight, what should happen out there? They should all meet, and my circumcenter is going to be out there somewhere. So is the circumcenter always going to be inside the triangle? No. Again, circumcenter. Might want to write this down. Circumcenter could be where? Can be inside, outside, or on. Inside, outside, or on triangle. So let's go back. Centroid. Where's the centroid always going to be? Inside. Orthocenter, is that right? Where's the orthocenter going to be? Could be any of them, right? Inside, outside, or on. Circumcenter could be inside, outside, or on. The last one. Angle bisector. Just tell me what an angle bisector is. Splits angle into two congruent angles. Don't make me take your toy away from you, Dalton. Show me some maturity. Splits an angle into two congruent angles. Point of concurrency for angle bisectors. What's point of concurrency? In center. What's that tell you? It's in the center. Guess what we're going to write next. Where is the in center always going to be? In center is always inside. In center is always inside triangle.
How do we put these in our binders?
Give it a second.
Like clipping these?
Did the in center have a theorem?
Yes.
So in center theorem. In center theorem. What did it say?
The in center of a triangle is equidistant from the sides of the triangle.
In center of a triangle is equidistance. I started writing it already. Is the same distance, right?
Yeah.
Is the same distance from
Sides.
three sides of a triangle. Three sides of the triangle. Now again, this one's sort of like the other one. It's sort of tough to see here. This is my in center on this triangle. I actually went through and I bisected each of these angles. Alright, I bisected each angle, drew it in here. Notice that the in center fell right here. You can't, it's not this distance that we're looking at. Alright, that's not the distance. How do I set up the distance? If I can tack this up here real quick. How do I find the distance from that in center to this side of the triangle? What's it got to come over here and form? It's got to form a right angle. So it would actually look, and I don't want to write on my triangle, it would actually look, I guess I'm going to have to, so that I can explain this to Owen. It would actually come up here and look something like this. It's going to come up here and it's going to form a right angle. Then it's going to come down here and form a right angle. This one looks like it's going to be somewhere pretty close to what's already on there. Then it's going to go to this side over here and it's going to form a right angle. Those three pencil line or segments that I drew right there, what do we know about all three of them? They're all congruent. Now does that mean this, and this are congruent? No, just the pencil ones. So with in center, with some triangles, you'll draw in the in center and all that stuff, and it'll come out to where it's the lengths that are on the triangle. Some others it won't be. Sorry, I'm erasing this noise that I had to write on my triangle.
Good job, Mr. Universal.
Ah!
Oh, no, stay tuned. Hey, I'll learn someday. You know, not many teachers can do it.
Just sweet.
Just sweet Tracy. I don't think she likes it. She gives everybody in our class bad grades, but like one person.
That's Joel.
She said, no, what?
No.
This week. His brother takes like 30 minutes. Just week for everybody had trigger.
Come now.
Yeah.
I'm so
Write that down. I know it's hard to see,
I
but
just took a picture of it all for the page.
as long as you know what it is. You guys coming in tomorrow then? Tomorrow?
Oh, boy.
I was talking with Wyatt, it'd probably be orange days would probably be good because you have Neil Brown.
Good, I can National Trail High School with a couple end of the day announcements for you. First one, say good luck to the girls basketball team tonight as they travel to Newton.